तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Alright, let me today start off on a slightly new topic, because I would like to spend some time giving an application of quantum mechanics, a practical application specifically in quantum optics and photon statistics, and this is one of the applications. There is a large number of such applications, but I thought this would be useful and a good takeoff from where we have stopped. We have studied a little bit about the harmonic oscillator and its properties as an exercise in quantum mechanics, and we have also done a little bit about spin half. I would like to combine these and talk about two level atoms and models of atom radiation interaction. To set the stage for that, I would like to introduce you to where the harmonic oscillator plays a role in understanding the behavior of the electromagnetic field, so the quantized electromagnetic field. A little preamble. We saw that you could start with classical mechanics, particle mechanics, and then do quantum mechanics by converting Poisson brackets into commutators. The natural question that arises is, what happens if you start with a classical field like the electromagnetic field, and would it have a corresponding quantum mechanics, quantum version or not? This is really the purview of quantum field theory, which is not part of this course, but I would like to point out that there is a simple way of understanding how the harmonic oscillator plays a fundamental role in quantum field theory. So I am not going to do the quantization of the electromagnetic field, but I am going to introduce the results in a very simple physically appealing way, and then at some stage we will make a little we will make certain assumptions which will tell you how the quantization actually occurs, and after that we will study the consequences of it. So what we intend to do is to understand how photons behave in a quantum mechanical way. So let me start by writing down Maxwell's equations and then imposing certain boundary conditions on it to get you familiar with the idea of quantized modes. Now recall that Maxwell's equations, so let me call field quantization, and I will put it in quotation marks because it really is going to beg the question. I am really going to assume the answer, but at least motivate what the steps are. Okay. Classically, if I look at the electromagnetic field in the absence of sources, so pure electromagnetic field, radiation field, then the equations, as you know, are del dot E is 0, no sources in a region without any sources or currents, del dot B is 0, del cross E is minus delta B over delta T, and del cross B is mu naught epsilon naught delta E over delta T. These are the source free Maxwell equations in free space. Okay. And as you know, it is easy to show from here that both E and B obey the wave equation, and the speed of these waves is given by 1 over square root of mu naught epsilon naught. That is the speed of light in vacuum. Okay. Now suppose I consider propagation of these waves along the z direction. So this is the z axis between two conducting plates placed in the xy plane. So this is x, this is y, and that is z. So we have a right handed coordinate system, and let us suppose that at z equal to 0 and z equal to L I have two parallel plates which are conducting, very large plates which are conducting, and look at what happens to standing electromagnetic waves in the region in between these two plates. Okay. The electric field must be 0 at the plates, at the conducting plates, they are earthed, and now I am going to assume that the radiation is polarized along the x direction. So I am going to assume that E, the electric field as a function of r and t, is just Ex times the unit vector in the x direction. So the electric field is along this direction, and since it is radiation, the magnetic field would be along the y direction, and the direction of propagation is z. As you know, E, B and K, but K is a propagation direction for electromagnetic waves, they form a right handed triad. The unit vector in the E and B directions, if you take the cross product, you get the unit vector in the direction of propagation. So this is Ex, and that is a function of z and t alone. And similarly, the magnetic field B of r and t is Ey By, and that is a function of z and t alone. So I am looking at plane polarized light. The plane of polarization is the xy plane, and the direction of polarization is the x direction for the electric field. Now these fields have to obey these equations here, and it is easy to see that suppose I put this whole thing in a cavity of volume V. I have not told you what the boundary conditions on these sides are, but we will assume it is some very large container of some kind, some cavity with some volume V. Then Ex of z and t is of the form sin kz, where k is the wave number of this propagation, and it is going to be such that sin kz is 0 at z equal to 0 and 0 at z equal to L. Those are the boundary conditions, times a normalization. So let me write down the solution. Equal to with this normalization I would like to get this right, if the angular frequency is omega and the wave number is k, then 2 omega squared by V epsilon naught to the power half, that is the normalization factor, and then some time dependent factor which I call Q of t. So these are some constant factors. This is the angular frequency of this mode, k is the wave number, and the two are related as you know by omega equal to Ck, and V is the volume of this container, epsilon naught is the constant that appears in these Maxwell equations. Q of t has the physical dimensions of a length. That is how I chose my normalization constant, and you can check that this quantity has the right dimensions for the electric field, and this is dimensions of length here. Then if you put that into this equation, and you solve, then delta E over delta t will have a Q dot of t, and that is del cross B, and B we already know is in the y direction. So if you work it out, the del cross B is going to bring out a factor k, so it is By of z and t turns out to be mu naught epsilon naught divided by k. That is because the del operator is going to produce a factor k that comes down the denominator, times 2 omega squared over V epsilon naught to the power half Q dot of t, and then this is a cos kz, because it involves a spatial derivative, becomes a cosine. Okay. Now it is a simple matter to check that these solutions actually satisfy the Maxwell equations here. Now what are the possible values of k? It is clear that k must be such that sin kl vanishes at this end. So k is quantized, k is equal to n pi over L, n equal to 1, 2, 3, etc. It is like waves on a string clamped at two ends. Okay. So far so good, we just have a classical solution of Maxwell's equations. But if you put these into the energy of the system, the Hamiltonian, now what is the energy density of the electromagnetic field? What is the energy per unit volume? It is half epsilon naught E squared plus 1 over mu naught B squared. So the total energy is equal to 1/2 integral over the volume, the energy density, and the energy density is epsilon naught E squared plus 1 over mu naught B squared. And you put this in and perform the volume integration. We have conveniently chosen things so that you get a 1 over V to the half here, and when you square it you get a 1 over V, which cancels the volume integral there, and then when you do this you end up with 1/2 omega squared q squared plus q dot squared with precisely this. That reminds you of the harmonic oscillator. In fact, this problem is identical to that of the harmonic oscillator, by the way, where omega is any one of these numbers, see k, where k is n pi over L. So you have many modes possible, and let us look at any one mode, any particular mode, some given value of k, allowed value of k, then the energy in that mode is given by just a harmonic oscillator. In fact, it is a harmonic oscillator with mass equal to 1, m equal to 1 effectively. So instead of q dot, let me just write this as p, because mq dot is p, so half p squared plus omega squared q squared. So you can see where the harmonic oscillator is appearing by the back door in the problem of the electromagnetic field. E squared plus B squared is essentially like Q squared plus P squared. Okay. This is the way the field is quantized. I have not quantized the field, I have not started with canonical commutation relations and quantized it, but I am just motivating the fact that the oscillator would appear naturally in this fashion. It really appears from the fact that E and B for a given mode of the electromagnetic field act like the position and momentum respectively. So let us accept that is the way field quantization appears, and now what I am going to do is take a big jump and say that I am going to take P and Q to be operators as we do for the harmonic oscillator, impose the canonical commutation relation. So from now on, from this step on, P, Q and P are operators which satisfy IH cross times the unit operator. What happens then? It implies that the electric field and the magnetic field are operators. Ex and By are themselves operators. And we could ask, what is the commutation relation between Ex and By, for example? That would be related to the commutation relation between Q and P. You can write down explicitly what it is. Now we solve the harmonic oscillator by going over to operators A and A dagger, which are essentially Q plus IP and Q minus IP, and then we obtained a number operator A dagger A. We found the eigenstates of A dagger A, they were just natural numbers, and we associated a number operator. Exactly the same thing will happen here, except that this number operator now has a physical meaning. It is the number operator corresponding to the number of field quanta, or the number of photons. So straight away from the oscillator we go over to a picture where the electromagnetic field is pictured as a collection of oscillators, one oscillator for each mode of the electromagnetic field, and then the number operator corresponding to that oscillator is just the number of quanta of the field, number of photons with that particular frequency and wave number, and state of polarization. We have not talked about the polarization, I will come to that in a second. So if you go ahead and say at this stage we say let A equal to m has been set equal to 1, so it is omega q plus IP over root 2 h cross omega, and A dagger equal to omega q minus IP over 2 h cross omega. Then this goes over into h cross omega into A dagger A plus a half. As exactly as it happened in the harmonic oscillator. Together with, of course, we have adjusted this constant such that A with A dagger equal to the unit operator. And now the rest is just a copy from the harmonic oscillator. All we have to do is to play around with these operators A and A dagger, and we have a complete set of states, eigenstates of this and so on. Now please notice that this whole thing is for one mode of the electromagnetic field, a mode that is propagating in the z direction with the particular wave number k, which is one of these numbers, and a fixed state of polarization. In reality, if you wanted to describe the electromagnetic field, you have to be a little more careful than this, and that is not the total Hamiltonian. You write down a better Hamiltonian than this. And what is that going to be? Well, first of all, that even in this direction of propagation there could be two states of polarization. One of them, well, you can have two independent states of circular polarization for the photon, for the electromagnetic wave. One of them, if you resolve it into plane polarization states, you have an Ex and a By. So the electric field is along that direction, the magnetic field is coming out of the plane of the board. There is another linearly independent state of polarization which would correspond to Ey. So the electric field points along this direction and the magnetic field along minus Bx. So such that E cross B still gives you the direction k. So you have one with electric field here, magnetic field here, another in which the electric field here is here and the magnetic field is down there, and these are independent states of polarization. You can combine these two and form left circularly polarized and right circularly polarized corresponding to the electric field vector making a circle either in the positive sense or in the negative sense, it does not matter. So if I denote these two states of polarization, and I pointed out earlier that the two states of polarization correspond to two helicity states for individual photons, that is the connection there. Then what would the Hamiltonian actually look like? Well, the total Hamiltonian really would be a summation over the states of polarization, which could be either left circularly polarized or right circularly polarized. Let me use a symbol little s for the state of polarization, and then a summation or an integration over all allowed values of the wave number k, and that is a summation over all allowed values of n. But then we have assumed the radiation is propagating in the z direction. It need not, it could propagate in any direction. Therefore you must really sum over all possible k vectors as well, all possible k vectors as well, and for each of these you would have an h cross omega subscript k, because for a given k omega is ck, multiplied by A dagger k vector s, A k vector s comma s plus a half. For each mode, each wave number k you would have an A dagger and an A, and for each of the S values you would have an A dagger and an A. So those operators would have two labels, and this would be the total Hamiltonian of the electromagnetic field, this thing here. What would these commutation relations look like? These are independent modes completely, so it is clear that these commutation relations would go over into AKS with A dagger K prime S prime equal to independent modes. These operators would completely commute, but if they both correspond to the same mode and the same S, then the answer should be 1. So it is clear that this would be equal to a Kronecker delta, a 3-dimensional delta by the way, of K prime delta of S prime times the unit operator. So this is the start of field quantization. So we will start by postulating these commutation relations and then look at what the consequences would be. I am not going to do that because that is really the task of quantum field theory. We are not going to talk about that at all. We are going to come back here and ask what consequences can we deduce from just this thing here for a single mode. What does it look like? What happens if you put this in equilibrium with a heat bath, a thermal heat bath at some temperature, which will take us to black body radiation. Okay. But the crucial point, the crucial physical ingredient is that the electromagnetic field is also quantized, and the free electromagnetic field, we are not talking about it in interaction with anything at the moment, the free electromagnetic field acts like a collection of harmonic oscillators, independent harmonic oscillators in the quantum mechanical sense. Okay. What would physically in this picture, in any state of this field, what would this correspond to? AK dagger AKS. What would this expectation value correspond to? What would be the physical meaning in any state of this field? What would be the physical meaning of this? It would give you the number of photons, the average number of photons, it is a number operator of wave vector k and state of polarization S. Okay. And it would therefore, if you now integrated this over the range, some range in k, if it is continuous, then you get the intensity of this electromagnetic field in that range, but that is proportional to the number, as you can see. Okay. Now that we have this, let us focus on one mode and ask what happens. So let us write down, for example, what E does. Notice that we already have Ex of z comma t equal to 2 omega squared over v epsilon naught to the power half q of t. Now what is q of t? We already have these equations, so this says 2 omega q over square root of 2 h cross omega equal to a plus a dagger, and this is a root 2 omega there over h cross, so this multiplied by h cross by 2 omega is q. So q of t is a plus a dagger root h cross over 2 omega, so let us put that in. Yes. Yes, root h cross over 2 omega a plus a dagger sine kz which is equal to some amplitude, let me call it just E naught. The operator part I want to retain sin kz. Okay. This factor, this whole thing came from Q of t. The t dependence of this classical field I put in this factor Q of t. So that is true even here, there must be t dependence. So this means we are working in the Heisenberg picture. These operators are time dependent. So we must be careful. Let me write that down properly. So this is A of t plus A dagger of t. And this is some constant. What is the value of this constant? E naught. It has dimensions of electric field. So it is 2 omega, the 2 goes away, right. So h cross omega over V epsilon naught to the power half, just for reference. Okay. And similarly the magnetic field By of Z, this is the y direction field, so By of Zt is equal to, there was a mu naught epsilon naught over k, and then there was this 2 omega squared over V epsilon naught to the power of half, and then q dot or p. So what was p? 2ip over root of 2 h cross omega was equal to A minus A dagger. So the 2 becomes root 2 here and over I root h cross omega over 2. So if I put that in for p here, this was A minus A dagger over I, and then root of h cross omega over 2 cosine kz. And if I put this in, this becomes omega cubed, and the 2 cancels, this thing cancels. I can put this h cross inside here, so that goes away, and that is what it is. So let me call this whole thing B naught and write this as A dagger A of t minus A dagger of t over I cosine kz, and call B naught this whole amplitude mu naught epsilon naught over k. Oh, we can get rid of an epsilon naught too, mu naught over k h cross epsilon naught omega cube over V to the power of half, and this goes away. That is B of t. So now we have our quantized fields. Ex is a function of z and t for this mode of propagation is A plus A dagger, and B is A minus A dagger. As you can see, they play the role of position and momentum, so to speak, apart from some dimensional constants. Okay. We can compute the commutator of E with B. That is like the commutator of X with P, and you can see the commutator is going to be A with A dagger is going to give you 1, and A dagger with A is going to give you minus 1. You get a minus 2, whatever it is, and it is easy to work out the commutator. The question is, what is the time dependence like? What is the solution like? That is not hard to find, because there are many ways of finding this time dependence, and in this problem it is completely trivial. the Heisenberg picture operator dA over dt is equal to the commutator of A with h over IH cross at any instant of time, okay. And that is trivial to find because this is equal to 1 over I, or rather omega over I, because h is h cross omega A dagger A. So this is the commutator of A with A dagger A. The half part does not contribute to anything, and it is just this guy here, which is equal to minus I omega A, because A with A dagger is unity and there is an A which comes out and it is minus I omega A, that is it. And what is the solution to this? This implies A of t equal to, just the exponential, so e to the minus I omega t A of 0, okay. And that is all you have to put in here. Similarly, A dagger of t can also be computed, but it is just the Hermitian conjugate of this, so it is A dagger of 0 e to the I omega t. This is just a C number, so it does not matter where I put it, but just sheer force of habit, the moment I take a Hermitian conjugate I invert the order here, it's in this fashion. So all you have to do is to put that in here and you have the exact solutions where A and A dagger are Heisenberg picture operators. By the way, you can solve this in another way. You know the formal solution to this equation, it involves the exponential e to the IHT on the left, and on the right you put that in and take the Adamar lemma and you expand it, etc. Find all those multiple commutators and eventually you will end up with exactly the same solution. Okay. Now the question is, what is the expectation value? Now I am going to say A dagger A on n is n on n, and n is 0, 1, 2, etc. The number n, the eigenvalue n, I identify with the number of photons in this state n, number state n. Is a number state n, in other words a state of this radiation field in which the number of photons is given, is sharp, is that also an eigenstate of the electric field? So the question being asked is, the Hamiltonian is h cross omega A dagger A plus a half. This is the number operator and these are the eigenstates of this number operator. So the question asked is, in a state in which the number of photons is sharp, is fixed, is precise, is that also a state in which the electric field is known precisely? No, because A and A dagger do not commute with A dagger A. Similarly, the magnetic field also is not known precisely. In fact, you can ask, what is the uncertainty in this state? What is the uncertainty in the electric field in a state in which the number of photons is fixed? What is the uncertainty in the electric field or the magnetic field? How would you do this? Well, all you have to do is to compute the expectation value of Ex in whatever state you want. And what is this equal to? Well, in this number state n, it is Ex n, and what is that equal to? What is the expectation value of A or A dagger in a given state n, number state n? So this is some constant, this is proportional to n A plus A dagger on n. What is this equal to? 0, because A acts on n and lowers it to n minus 1, A dagger acts on n and raises it to n plus 1. So A and A dagger now can be called, previously we just called them raising and lowering operators, A dagger and A, now I call them photon creation and photon destruction operators, because a dagger acts on the number state n and makes it n plus 1, in other words it creates a photon, and a destroys a photon, it reduces the number of photons by 1. Since these have no diagonal elements at all, this is identically 0. So the average value of the electric field is certainly 0, but the mean square value is not 0, definitely not 0. What is the mean square value? Ax squared equal to, well, we have got a formula for this thing here, so it is E0 squared sine squared kz times a plus a dagger squared, so n a plus a dagger squared on n. Now what is this equal to? So you should be able to compute these expectation values fast. What is that equal to? Huh? Yeah, it has got to become proportional to n plus half, because this term here is a squared plus a dagger plus a dagger a plus a dagger squared on n. A dagger squared on has no diagonal elements, that is 0, a squared has no diagonal elements, that is 0, a dagger is a dagger a plus 1. So this can be written as a dagger a plus 1, but a dagger a on n is just n times n, and therefore this works out to be equal to E naught squared sine squared kz times 2n plus 1. Okay. Therefore in this number state, delta Ex in the number state n is the standard deviation, that is the square root of this guy. So this is equal to E naught sine kz modulus sine kz, if I take the square root, times root of 2n plus 1. So it tells us very crucial. By the way, what is Bx going to be? What is the By, the expectation value of By? What is this going to be? Well, it is clear that once again the square of these guys is going to give you 0, and let us quickly compute what the expectation value of what delta By is. Delta By whole squared in this number state n is B naught squared minus, because I have a minus here, and then cos squared kz, then expectation value of a dagger and a dagger a, both with minus sign, so this minus sign goes away, and that is just going to give me a 2n plus 1. So delta By in this number state n is equal to B naught cos kz root 2n plus 1. And the important thing to see is that even in the ground state, even in the 0 photon state, the uncertainty in the electric field and magnetic field is not 0. So there are vacuum fluctuations. These are called vacuum fluctuations, because in a quantum field it is very subtle. Even in the state in which there are no quanta present and you have a vacuum, nothing at all, there is still a fluctuation of the electric and magnetic fields, and they have physical consequences. This has a physical effect which is measurable. So note not identically equal to 0. They are still vacuum fluctuations. One of the physical effects is the following. If you took two parallel plates as we have done here at z equal to 0 and z equal to L, conducting plates, then even in the absence of an electromagnetic field in the region between them, there would still be a force between the two. There would still be a force of attraction. This is called the Casimir effect, and it happens because of the 0 point energy. Notice that there is a 0 point energy in this problem, and it is formally infinite, which is completely crazy, but then this is an artifact of quantum field theory. The energy, the ground state energy, equal to, when n is 0, we know the energy is h cross omega into n plus half, so it is actually h cross omega over 2 per mode. Every mode contributes an energy h cross omega over 2. So every wave number contributes an energy h cross omega over 2. Two polarizations, the factor 2 goes away because there are two such contributions, and then you have to sum over all possible omegas, and that is infinite, right, because the number of k's is actually infinite. So the 0 point energy of the electromagnetic field in a vacuum is actually infinite, formally infinite. But you could ask, for this force, this real force between two plates, how do I compute it? Well, I put the whole thing in a box, sufficiently large box. So I take the side walls of the box to be very large and the distance between the two plates to be small compared to the dimensions, linear dimensions of the side walls, and I ask what is the energy it takes to bring the second plate from infinity up to a distance L. The difference in these two 0 point energies will be the work done in bringing this plate out here, and from that if you take a gradient you end up with the force, and you can actually compute this force, and it was experimentally measured in the 1950s, and there is such a force. This effect is a very real one. It is a delicate experiment because you have to make sure that you got rid of all the other effects, and the conditions of the experiment have to satisfy the assumptions made in deriving these expressions, but this has been done. And this force, this ground state energy, the 0 point energy, leads to a real force. It is called the Casimir effect. Okay. It has been experimentally seen. There are other effects, quantum electrodynamic effects. One of them is the famous Lamb shift, which occurs in the spectral lines of atoms, including that of hydrogen, and that too has been experimentally verified to a high degree of accuracy. So we are confident that the quantization prescription is actually a correct one, and this is the way the electromagnetic field behaves. Now I leave you to figure out what the uncertainty products are for n, for Ex, Ey, what the commutators are, and so on and so forth. Notice that you must have definitely in any state you must have delta Ex, delta By is greater than or equal to 1/2 the magnitude of the commutator of Ex with By, of the expectation value of the commutator in that state. That is easily verified in this case. Okay. Any questions so far?
Expectation value of Ex square
Yes.
is proportional to 2n plus 1.
Yes.
If n equals to 0, then also we will get expectation.
Then also you get an expectation value.
And
This is a vacuum fluctuation.
Yeah, and we have theorem that expectation values are the values which we are, if we will look at classical analysis, then also we will get.
Yes, these are the values which you will experimentally obtain. Yes.
And classically also.
When you make a measurement, this is what you expect. Now, one thing is very clear, that when you make a measurement, a single measurement on any physical observable, the postulate of quantum mechanics says the answer you get is one of the possible eigenvalues of this operator. We haven't said anything at all the expectation value we have there is in the number operator state. We haven't said anything at all about the actual eigenvalues of A and A dagger, or eigenstates of A and A dagger. We haven't talked about that at all, but we know in the classical harmonic oscillator that the spectrum of X is actually continuous, the spectrum of P is actually continuous. So these operators Ex and By actually have continuous spectra. When you make a measurement, you are going to get one of those answers, one of those numbers, you do not care what it is. What we are now saying is, if you prepare the system in a state of a definite number of photons, then you measure what the expectation value, the uncertainty in the electric field is, even in the ground state, even if there are no photons, the answer is non-zero. That is the statement being made. Is this clear? Okay. Now of course you could ask, in a real black body cavity, what happens? What kind of radiation do you have? It is certainly not standing waves operating in one direction or anything like that. There is a whole admixture. So let us do that. Although this is part of quantum statistics, let us do that by our sort of heuristic method of counting, which we kind of we more or less beg the question, but we will get the right answer. Let us do it in this informal way. Okay. Now there are several other questions which I will come back to here, which we need to answer. One of them is, in the case of a classical electromagnetic wave, I have an amplitude as well as a phase, and then interference effects happen because of this phase. What is the quantum analog of the phase? This is a very, very important question, and we will come and talk about it in a minute. The second question is, Ex and By in some sense are like the position and the momentum, and therefore they are conjugate variables. The commutator of Ex and By is like the commutator of X with P, it gives you IH cross times 1 and so on. What about N, A dagger A? What is the conjugate variable to A dagger A? In other words, what operator should it be such that if you now take A dagger A commutator with that, you get unity on the right hand side. Now what kind of operator would that be? What is the conjugate of A dagger A? Now if A dagger A is taken to be the amplitude, the square root of A dagger A, if you like, is taken to be the amplitude, the square root of the intensity is like the amplitude, then the classical assumption, the classical intuition tells us that there is the amplitude and the phase. Therefore there must be some phase operator somewhere, and maybe this is the conjugate of A dagger A. Let me show that that is not as simple as it seems, and then we will do black body radiation, come back and talk about the phase of this operator, because I would like to introduce the idea of coherent states and go on with quantum optics. So let us try and see what happens if you try to define a phase. You run into trouble as follows. So let us put A equal to, I have this quantity A dagger A, that is the number operator. This is now an operator, so I would like to use a symbol for it which is appropriate. I do not want to use little n, which looks like the eigenvalue. I want to use, otherwise I put a caret on it or something, but instead let me just call it, this is the number operator. So just as I take a complex number z and write this as r e to the I theta, where r is really the square root of zz star, the modulus, in exactly the same way, instead of z star, instead of z I have A, instead of z star I got A dagger, and I have this combination mod z squared, which is really A dagger A, that is a Hermitian combination. So let me write this as equal to, let me see what the standard notation is for this, e to the I phi square root of n. Let me say I define A, I do a polar decomposition of A, just like I do a polar decomposition of complex number, I do a polar decomposition of this operator A by writing it in this form. And then what is a dagger? Phi is supposed to be an operator now, and n is an operator. So this becomes square root of n e to the minus I phi. So let us see if this works or not, and the commutation relation is a dagger minus a dagger a equal to the unit, equal to 1, the unit operator, or 1. So this implies that e to the I phi n, this n with this root of n gives you an n, e to the minus I phi minus a dagger a is n, because a dagger is root n, e to the minus I phi, e to the I phi root n, and the e to the minus I phi and e to the I phi, they commute with each other, give you 1, and you end up with this n, and this must be equal to 1. So this guy here, let me call it the phase operator, okay, and put a question mark to see is this really sustainable or not. This was Dirac's idea originally, that you do this polar decomposition and see if you can consistently define a phase operator of this kind. Then this commutation relation between a and a dagger, the canonical commutation relation, which I remind you came from the original xp is IH cross, goes over into this here. Now what would this imply? Well, you have to take this operator, expand it, and so on and so forth. So let us do that. E to the I phi is 1 plus I phi minus phi squared over 2 factorial dot 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 with n, and then 1 minus I phi minus phi squared over 2 factorial dot dot minus n should be equal to the unit operator, and the n cancels out on both sides and you get I times, there is a phi n here and then the minus n phi equal to 1, or it looks like this is sustainable if I define n phi equal to 1, equal to I. Okay. So it looks like we are almost there, because just as I had a with a dagger equal to 1, I have n with phi equal to I times the unit operator. You can check that if I have this commutation relation, then all the terms here, this entire relation is satisfied, this relation itself is satisfied. Okay. I picked this off by asking for the first term linear in phi, but you can look at the higher order terms and all of them would be satisfied if this commutation relation is valid. Okay. So it looks like we are in business. You can write a in this form, a dagger in the polar form, and then n and phi are complementary to each other in the sense that the commutation relation between the number operator and the phase operator is in fact just I out here. Now of course if you want these to be physical operators, you want this operator to be Hermitian and you want this to be Hermitian. In other words, you want e to the I phi to be a unitary operator, right? Otherwise it does not make any sense. So you would certainly like this to be a unitary operator. Okay. Now what happens if you if it is a unitary operator, it means u dagger is equal to 1 and u dagger u equal to 1, but the question is this really true? Look at what happens. E to the I phi equal to a n to the minus half. If I operate with n to the minus half on the right hand side, I get e to the I phi is a n to the minus half, and if I do the same thing here, e to the minus I phi equal to n to the minus half A dagger. If this is an operator U, a unitary operator, I expect this to be U dagger or U inverse. This is U inverse and I want this to be U dagger for it to be unitary. So what happens if I put it in? U inverse, if I put that in, this gives me equal to A n inverse A dagger, and that is not identically equal to the unit operator, by no means. On the other hand, if I do U dagger U, you get n to the minus half A dagger A n to the minus half, but this is n to the minus half n to the minus half equal to the unit operator. So here is our first indication that everything is not alright, because these are infinite dimensional Hilbert spaces. There is no guarantee that if there is a left inverse there is also a right inverse, and if something is unitary you require not only that U dagger be equal to I, but also U dagger U be equal to I. But with this set of operators you end up with U dagger is not 1, but U dagger U is the unit operator. So you begin to see there is already a problem. The root of this difficulty is, of course, this is an infinite dimensional Hilbert space and you have to be very careful here. There is another way of seeing this, and that is if you took the expectation value of this relation here, or if you like if you took the expectation value between number operator states of this relation, for instance, between number operator states of some kind, then you run into a difficulty. Let me see what is the easiest way of seeing that. Yeah.
Can't we write n inverse as 1 by n?
Pardon me? Yeah, it is. I mean, okay, 1 over n does not have any meaning, 1 over an operator does not have any meaning. By that you mean n inverse, the inverse of the operator.
Then we write if 1 by n equal to 1 by a dagger, then it cancels out to get.
No, you can't do that. No, these are not numbers. No, these are not numbers, right? You can't do that. No, he is suggesting you do a 1 over a dagger a. If you have an a dagger a, then he says you cancel this with this. No, no, these are not numbers, these are operators of some kind. I have already been quite careless here. Why have I been very careless here? Tell me. N may not have an inverse. What is the spectrum of n? 0 is an eigenvalue. 0 is an eigenvalue. So if I wrote this as an infinite dimensional matrix, then in the eigenbasis of this operator n, it is a diagonal matrix with element 0, 1, 2, 3, etc. The determinant is 0. Of course you may say, look, you are going to do 0 times 1 times 2 times 3, etc. up to infinity, so how do you know it's 0? So there are technical difficulties here. So you can't play around in this very casual fashion as we have done, but the fact is this is a real problem. There is a difficulty here. That also comes out if I took this thing here and asked, let me take the expectation value of this with number things here. So we have said n phi minus phi n, and I take this between the state n and a state n prime, and that is equal to n prime, the unit operator n, and there is a factor I. But this quantity I know is I delta n prime n, because these are orthonormal states. On the other hand, when this n acts on this n prime, you get an n n prime. So there is an n prime from here. When this acts on that, you get an n, then the matrix element, go to this. If this commutation relation is true, then that is true, that statement is true. But what happens if n is equal to n prime? This is 0 and that is equal to I. So you immediately see this commutation relation is not sustainable in this Hilbert space spanned by these states n. So although it looked as if you had no difficulty in writing a phase operator in this fashion, really this is not sustainable. This operator cannot be a physical Hermitian operator, because if it were, this is a unitary operator, but we have seen explicitly it is not a unitary operator. You have difficulties. Besides, the commutation relation between n and phi is not maintainable. This leads to an inconsistency. It says 0 is equal to I to start with. So there is a serious difficulty in defining the phase operator in quantum mechanics. Classically there is no difficulty at all, and this has arisen for a variety of reasons. One is an infinite dimensional space. Secondly, it is not very clear how to define a physical phase operator here. Does it have any meaning and so on? Can I do it consistently, etc. There are several resolutions that have been proposed, and we will talk about just one of those things to get over this mathematical difficulty, and it brings out the fact that these crazy operators in this infinite dimensional space sometimes could have a left inverse but not a right inverse and so on. Okay. So we won't spend too much time on this. The reason it is important is because you do need to know what is the phase of the electromagnetic field, what do you measure classically, what does that correspond to, what expectation value does that correspond to, that we need to answer, and we will do that. And then the first thing I do next time is to talk about what happens if you have a radiation field inside a black body radiation, and we will talk about the photon number distribution in black body radiation, and then go over to the interaction of atoms with radiation with matter. We will look at some simple model for it which will help us make connection with the spin half problem. Okay, so let me stop here today. And, tomorrow's lecture is not